So good morning, everyone, and welcome to today's webinar on material models in GEO5 FEM. My name is Tomáš Janda, and I am one of the GEO5 FEM developers, and I also provide the technical support for this software, and I answer most of the hotlines. You can always reach me at my email tomas.janda@fine.cz. With the outline. First, we will look at two types of laboratory tests that are quite useful to calibrate the material models for the FEM analysis. Then I will go quickly through some essential families of material models that are implemented in the software, which are elastic models, elastoplastic models, potentially with hardening or softening, and finally with the critical state models like chem clay or hypoplastic clay, which are a special kind of elastoplastic models for granular materials. Then I will mention the feature bringing the depth dependency of stiffness, and I will also show you how to create a geostatic stress, what is the K-knot procedure, and how the Poisson ratio influence this process. And finally, I will mention some possibilities how to calibrate the material models or how to obtain the material parameters. Okay, so in this talk, I will mention two laboratory tests which are quite, I would say, prominent in when you deal with some constitutive law or some material model. These two laboratory tests are Endometric test, which is sometimes called 1D constraint compression. This is, I think, one of the most basic laboratory tests made on source samples. And the second one is triaxial shear test, which can be drained or undrained. And the reason why we will model and we will discuss these two laboratory tests and not, for example, a direct shear test, which is this one, is because in these two tests, the stress and strain field within the specimen is homogeneous. So modeling, you can model, as you will see, you can model or simulate these tests with just one or two finite elements, which is not true for the direct shear test, where some shear band of unknown thickness on unknown width appears. And because we don't know the thickness, we don't know the displacement field and the strain field within this sample, and to get some information about the material point is quite difficult from tests like this. It's not impossible, but the simulation is more difficult than the simulation with these two tests I mentioned. Okay, so the Endometric test, as I said, is a 1D constraint compression, which means that the lateral strains are 0 and the lateral stresses are unknown because we don't measure these in the typical Endometric test. And the vertical stress and vertical strains are known. One of these is prescribed and the other is measured. And what you receive from these tests are graphs like this. So there is some primary loading, then unloading, then loading again. And so these are real data from a real Endometric test. Sometimes this test is also called consolidation test, but I'm used to use the word consolidation for a coupled problem where there is some pore pressure dissipation and it's some time dependent problem. So this test is not time dependent. Of course, it is measured with some during some time. But we assume that the pore pressure is known or 0. And this another graph is a graph of the same data. These are the same data, but these are just redraw in let's say more classical or more classical way in terms of mechanical or response of general materials. So axial strain on horizontal and stress on vertical axis. So you can see that the soil, the response is highly non-linear. There is, it looks like this. The reason why this is linear is because we have a logarithmic scale for stress. So this is Endometric test. Then we have a drained triaxial shear test. We sometimes use this abbreviation CID, which stands for consolidated isotropically with volumetric strain measurement. And again, these are some real data from this test. You can see that there is some softening and there was compression at the beginning and then some dilatation in this softening part. So because we measure the volumetric strain, we can see that the soil is like swelling a little bit. And then we have this undrained triaxial shear test, which is sometimes abbreviated as CIUP, which means isotropically consolidated, undrained with pore pressure measurement. Again, from this test, we get some results. These results, as I said, are for undrained conditions, but these are typically drawn in terms of effective stresses. The advantage when compared to the drained test is that you can perform this test on some clay samples, and you don't because the water does not have to flow from out of the specimen. It can be performed in shorter time. But anyway, doing undrained triaxial tests takes some time anyway, because we have to ensure that the pore pressure is homogeneous. So we know how the pore pressure evolves during the time, and we can calculate these effective stresses. Because the soil is saturated and undrained, the volumetric strains are 0, and such test can be simulated, as you will see, quite easily with prescribed displacement. When we prescribe displacement so that the volumetric strain is 0, we basically simulate the undrained triaxial shear test. So let's jump to the material models, and first we will look at the elastic model, which is quite trivial. The stress tensor is related to strain tensor with I will use this one with this so-called isotropic with this so-called elastic operator. And if this law is isotropic, which is what is implemented in the software, then this operator is determined by just 2 elastic constant, which can be, and in the software then these typically are chosen to be Young's modulus, denoted as elastic modulus in the dialog, and a Poisson ratio. And the other elastic modulus that you know, like shear modulus or bulk modulus or Endometric modulus, are then dependent on these 2 selected elastic constants. So as I said, shear modulus is then related to E and Poisson ratio by this formula. The Endometric modulus, which relates the vertical stress and vertical strain for the Endometric conditions. This modulus is also called a P-wave modulus. If you search for it, let's say on Wikipedia or something, you will find the Endometric modulus to be the same as this P-wave modulus. And it's related to E and Poisson ratio by this formula. And finally, bulk modulus relating mean stress and volumetric strain gets this this term. Okay, and here you have just these formulas in some visual form. This is how the shear modulus, how the endometric modulus, and how the bulk modulus depend on Poisson ratio. And of course, if the Poisson ratio goes to 0.5, then the material is incompressible in the volumetric sense, and these two modulus goes to infinity. Another kind of elastic, or I would say hypoelastic model implemented in the software is so-called modified elastic model, and in this model you enter elastic modulus, which is the primary elastic modulus or modulus for the primary loading, and then you enter the modulus for unloading, reloading, which has to be higher. And then if you simulate, let's say, endometric test, you have this primary loading branch, some unloading, primary loading, and again some unloading to some lower value. So this model, let's say, remembers in some history the highest stress, or the norm of the highest stress that it experienced. Then we have elastoplastic models, and I would say the most commonly used model in geotechnics is a Moore-Coulomb model, which has some elastic domain, which is within this cone. The cone is defined by these 6 yield criterions, and you have to enter angle of internal friction and cohesion. And in this simplest form, the model is elastic and perfectly plastic. Again, this is drained triaxial shear test. So before we reach the yield function or the yield boundary, it behaves elastically. So for loading and unloading, it would go along this line, and as soon as you arrived, or as the stress arrived to this boundary, it starts to yield without changing in the stress. And then when you unload the sample or the specimen, you will end up with some permanent strain. Again, you can use the unloading reloading modulus for this model as well. So then we have a modified Chemclay model, which compared to the simple modified Moore-Coulomb model, allows for either softening or hardening, and the softening or hardening is defined by some piecewise linear functions for internal angle of internal friction or cohesion, depending on the elastic deviatoric strain, which means basically as we shear the sample, these material parameters can evolve. And you enter this with such dialogue, and you are presented in the software which chart or with a graph representing what you have entered. So, for example, this is some softening part, and then perfect plasticity over here, and a simulation of drain triaxial test corresponds to this. So this is elastic part, and then softening here and perfect plasticity without a change of the deviatoric stress in this part. And the final class that I will mention today is a class of the critical state elastoplastic material models, which is a modified Chemclay model or a hypoplastic model for clay. And in this sense, it is quite useful to understand what the concept of soil states represents, or what does it, what do we mean by soil state. So if you imagine some granular material, some let's say sand, and you have this sand in a loose state. When you start to shear it, or you can load this this material by some isotropic stress, these 4 forces, and when you start shearing, it contracts. So there are some volumetric strains or volumetric changes that are brought to this specimen by just this shearing. This is because we the grains reorganize so that they fit better together. So there are these volumetric changes. But on the other hand, if we have a very dense soil, let's say some over-consolidated, very dense sand or clay, and we start to shear it, it starts to dilate, because if the grains are forced to move relative to each other, they have to make some space along them, so they have to dilate. So this is the let's say response for a very dense soil. And we have some material parameters, and we have some parameter that can evolve during the straining, which is so-called state parameters, which is not a constant. And this can be either a preconsolidation pressure or a void ratio of the soil. So we have some parameter that will evolve not only stress, but also this state parameter. These 2 models are, or the deformation response is defined by this this diagram of isotropic compression, which basically tells us how the soil reacts when you load it isotropically. So let's say we have some loose soil with some initial void ratio, and as when we load it by some isotropic pressure, the void ratio decreases. When we then unload it, it increases again, but along this kappa line. This is a primary loading line, and this is unloading loading line. And again, this is defined in a logarithm of the mean stress, in which this is a linear, but as you saw on the slide with Endometric test, it is non-linear response, of course. And what this formulation means, or what can be derived from this formulation, is that the tangent bulk modulus of such material, the elastic bulk modulus, depends on the current level of stress or mean stress. So this basically means that soil that is stressed more is stiffer than soil that is not stressed that much. Okay, because these models are elastoplastic, they have to have some, or the modified Chemclay model is elastoplastic, so it has some yield function or yield boundary, which is elliptical. It is given by this MCS, which is a slope of this critical state line, which depends on angle of the critical angle of friction, and its state is given by this preconsolidation pressure, or OCR, which is over consolidation ratio. And again, from this figure, you can see that if the soil is highly consolidated or over consolidated, we arrived to this elliptical boundary, and due to the dilatation, the stress goes down, or if we are in the subcritical domain, at this point, there is compression, so the deviatoric stress can go higher. So there is hardening of the material. Okay. So this is just some simulation done with modified chemical model with OCR equal to 1. You can see that the response is non-linear over here. Some unloading, reloading, again unloading. And finally, there is a hypoplastic model for clay, which is formulated within the theory of hypoplasticity, which means that there is no plasticity boundary, but the model is formulated only in rate form. This is from the user's perspective. This means that you can't see elastic and plastic strains in the results. You have there are no plastic strains, but the response is non-linear, as you can see over here. And the advantage of this model over the modified ChemClay model is that it prevents some tension, for example, over here. And in the deviatoric domain, it resembles more Coulomb model. So it tends to fit the behavior of real soils in a wider range better. Okay, so before I go to geostatic stress, let me just create some example models. And in the software today, we will, or I want to show you how to prepare this Endometric test and this undrained triaxial test, and how to run these simulations, and where to view these charts that I have presented. Okay, so let's start with GEO5 FEM. I just save this as Endometric, so I will create Endometric simulation of some Endometric test. First of all, I go to settings. Probably I can leave everything as it is, because Endometric test can be simulated as a plane strain problem. There are no out of plane displacements or strains, so this is correct. I go to interfaces, and I create Endometric of, for simplicity, can be 1 meter by 1 meter. So I will put 1 over here and 1 over here, and then I add interface here and here. Click OK, and you have this 1 meter by 1 meter square. Then I go to soils, and I add some soil, and let's say we can use a modified ChemClay model and leave these default parameters for now over here. And because we want to have this homogeneous displacement, homogeneous strains and stresses, I will choose that the unit weight is negligible. So I will just put a 0 over here. And this is modified ChemClay model. Okay, so this is like this. I think this should be also 0, but probably not necessary. I will make it color and create. Okay, so we have defined a modified ChemClay material model over here. Then we should go to assign, and it gets assigned automatically because we have just one domain and one material. So it's clear, but you have to click this button to assign it, and then we can go to mesh generation and just click generate mesh, and we have two finite elements, two triangular finite elements, which is enough because it's homogeneous. No need to have more of them. Okay, so then in the first stage, I think it's in experiments or in tests like this, I think it's quite okay to have not to define any surcharge or any loading in the first stage. We just check that when we run the analysis, everything should be 0 because the soil is in gravityless state, so we have no displacements, no stresses, everything is 0. Then I add another stage, and here the single thing that I will do is I will add a vertical surcharge on terrain, okay, starting at 0 and going to 1, and it will be vertical, and this could be something like 100 kilonewtons per square meter. Okay. And then I will add another 2 stages, which will be unloading and some reloading. So in the third stage, I will click this surcharge, and here I have to double click it. I click edit magnitude, and I reload it to, let's say, 20. Okay, and in the fourth stage, I have to again edit and again change it from 20 to, let's say, 150. Something like this. And then I go to fourth stage and run analysis. Okay, so we have some values, everything is homogeneous, no colorful images probably. Okay, but what is, let's say, there should be some vertical effective stress, 150. We can check it. There should be 20 over in here, 10, 100 in here, 150 here, etc. But I think what is more interesting is to use these graph features. But these graphs can be assigned only to some monitor points. So we have to go to monitors, and it doesn't matter in which stage. Probably in this one, we add. We just type where we want to observe the quantities, and because here it is homogeneous, it doesn't matter where we put it. So I put it in 0.5 and minus 0.1, for example. So at this point, I will be able to observe the evolution of selected quantities. And when I go to fourth stage, I think it's also a good idea to go to the last to the analysis again, and then check this detailed results, because if you don't have this checked, you are offered only to see these quantities, but when you check it, you have all these quantities over here, and these will be also offered you when you create the graph. So then you go to graph again, you go to, and graphically you select your point and choose what you want to see. So for example, effective vertical, or the first one, course of loading, is the let's say course of the stages, how the loading was added during each stage. So we select this one, and vertical stress. This is just to check that vertical effective stress is this one. select your graph, and here you can see that in the first stage, no change in vertical stress. Then you go up, down to 20, and up to 150. So this is what we have defined, how it changes during these 4 stages. Okay, so then we can add another graph graphically to this point, and probably what can be interesting is a horizontal is a vertical stress, a vertical strain, which is vertical strain and vertical stress effective. So this is the loading, unloading, and reloading branches. Probably it is also a good idea to go to first stage again, and then in analysis and settings, you can make the initial calculation step, or the calculation step to decrease this calculation step, let's say to 0.1, and run the analysis again, so that the line is a little bit smoother. Okay, graphs, this one. So now it's a little bit smoother. Loading branch, unloading, and reloading goes to along this kappa line and then the lambda line again. So this would be how to simulate and how to verify that, let's say you have these data from your Endometric test, you calibrate your model and you want to verify that you are using it correctly. So you can plot this chart over here by this graphs feature. And so I save this, and the second thing that I would like to model is the undrained triaxial shear test. So I save this as this CIUP undrained triaxial shear test. And I have to do some modifications. So I go back to topology in settings, because now we have to prescribe or allow some out of plane displacement. So we cannot solve it or we cannot model or simulate it as a plane strain problem. So I switch it to axisymmetry. It will be axisymmetric stress analysis. And I also have to check this advanced mesh generating parameters, because when I check this, I can prescribe or I can force the mesh generator to create just some 3-node elements which are necessary for the simulations to give a correct result. So then I go to mesh generator. I think everything else is identical. So I go to mesh generator, and here I switch off the multi-node elements. So I end up with just 3-node triangular elements, and then I run generate mesh. And again, the mesh looks identical, but if you look at the nodes in the previous model and in this model, you will see that these are just triangular elements. Okay, I think this is all what I go to assign. Okay, this is assigned, so I can go to first stage, and here I will change the boundary conditions. So I go to line supports, switch off these automatically generated supports, and I add graphically to a mesh line, which is this one. And here I want, because it's axis of symmetry, so there will definitely be no, it will be free in the, and it will be fixed in the X direction and free in the Z direction. Click OK, and then I will add this one. This will be fixed in the Z direction, fixed. So these are my new boundary conditions. And I go to analysis and run analysis, and nothing should happen. Everything should be 0. Effective stress. Then in the second, I will probably remove this. Then in the second, I have the second stage inherited the boundary conditions from the previous stage, so this is correct. And during the undrained triaxial test, we first load the sample by so-called chamber stress, which basically means that the isotropic consolidation that is the first stage is of course a drained problem. So we just prescribe some isotropic stress. Isotropic means stress for the samples, and this is done by defining a surcharge on the top, so on terrain, basically going from 0 to 1, and let's say this can be 100, something like this, 100 kilopascals, acting from the top downwards. But I also need to prescribe this on this lateral boundary, and this has to be done by using a general over here, and it goes from the point 1 and 0, which is the upper right corner, to the lower right corner, which is 1 and -1. And it's 100 at the beginning and at the end. So it could be a trapezoidal surcharge or distributed loading, but this is constant. So I have to put it like this. So I have 100 acting from the top and 100 acting from here. And that's it. We run analysis. And of course, vertical effective stress should be 100. Vertical stress is 100. Horizontal sigma x is 100. Mean stress effective is 100. Total is 100 as well, because there is we simulate this undrained test without water, without any pore pressure. We just prescribe the strains that correspond to the deformation that would appear if the soil is saturated, which means no volumetric strains. So this is some kind of trick how to model the undrained triaxial test directly. So then we add another stage, and here we will model the shearing stage, which means that we are increasing the load on the top and keeping the total stress laterally, but because it's undrained, we can model this by prescribing some displacement on the top and half of this displacement on the lateral boundary. So let me do this. I first get rid of this surcharge. And prescribe some vertical deformation of, let's say, 10 millimeters on top, and in the X direction, I also prescribe, let's say, -5 millimeters, which means outwards. So for this prescribed deformations, the volumetric strain is 0, because the volumetric strain is, or from these numbers we can see what the vertical strain is, what the horizontal strain is, and because the out of plane strain is also is the same, so we have 0 volumetric strain. Okay, and we just run analysis with these prescribed strains. And again, do we have this monitor point over here? Yes, we can go here and add graphically to that point how the vertical strain evolves, for example. Okay, course of loading over here and here. So this this means that it should be, maybe we can run the analysis with a little bit smaller steps. So I go to analysis again, I go here, settings, fine. So it will be a little bit smoother. Okay, let's go to graphs. So this is, for example, how this was the first stage. This was the first stage. Then there was vertical displacement due to the isotropic consolidation, and then there is also some small displacement prescribed linearly over here. Maybe another chart will represent better what's happening here. So I add graphically to this point another chart, another graph, and this could be, I think, let's say, how the vertical stress evolves. So let's say effective vertical stress, how it evolves with course of loading. Vertical stress is over here. Okay. So basically, this means that in the first stage, nothing. Then during the isotropic consolidation, the vertical stress increases to that 100, and then it goes down because this is normally consolidated soil. That then when we shear it, when we start shearing it, the grains would normally contract, but because they cannot contract because of the water in the specimen, the pore pressure carries some of this prescribed chamber pressure, and the effective stress goes down, which is this decrease in the effective stress. And finally, I think a useful graph could be this one, and graphically. Let's say again, course of loading, and how the deviatoric stress which is, let's say, some measure of the shear stresses in the specimen, how this evolves. And again, in the first stage, nothing. Then in the second stage, because of the isotropic loading, again, the equivalent deviatoric stress is 0 because there are no shearing, and then it starts then it evolves and it almost reaches some critical stress, because some critical state. The critical state is when you shear the soil, and the soil just shears to infinity, and the stress does not change. So here we are going close to the critical state. It contracts a little bit, and there are some redistribution, but finally it ends up shearing indefinitely, and like this. Okay, so I think this concludes this simulation, and I can go back to the presentation. So the geostatic stress is quite important stage in or important part of the analysis, and we have two possibilities how to create the geostatic stress. The first one is, it is selected here in, I think, topo settings. In the topo settings, you select geostatic stress or K0 procedure. If you choose a geostatic stress, this is a standard finite element analysis. You basically switch on gravity. You create your model, switch on gravity, and this is what happens. And the structure deforms somehow, and the stress you receive from this analysis is the resulting geostatic stress. Just be careful that the displacement are zeroed in the first stage. So if you do some experiment like we did now, it's useful to start with the second stage, so you are not confused why the structure does not deform and there is some strain, etc. And then there is a second approach, which is so-called K0 procedure. And in this, this has nothing to do with finite element analysis. You just compute a vertical stress from this formula, and then you set the horizontal or the out of plane stress by this formula, where K0 is either prescribed. You have to prescribe it in the soil dialog, or it can be computed from a Poisson ratio. And also be careful that the shear stresses are 0. So by running the K0 procedure, you may end up with stress field that is not in equilibrium. Okay, so what is the coefficient of lateral pressure? This is well known. So it's a ratio of the horizontal and the vertical stress. Of course, if you think of Endometric, and if you think of theory of elasticity, you will end up with this formula for K0, which means that when the vertical stress is prescribed, the horizontal would be nu divided by 1 minus nu. Yeah, that's it. This is a result of the theory of elasticity for Endometric, for example. And then there is some empirical formula. This Yaki's formula is this works for perfect plasticity and cohesionless soil, and the Yaki's formula suggests that the K0 is 1 minus sinus phi, and phi is the angle of internal friction. And again, here you can see how this K0 evolves with the angle of internal friction. Of course, when we have when we have a material that has that has 90 degrees angle of internal friction, it does not have to let's say doesn't push to the sideways, so the K naught would be 0. On the other hand, a material with 0 friction angle would be some fluid, for example, and for fluid the K naught is of course 1. And finally, another charts that I think are quite useful is that this K naught can be computed for the friction angle directly from this Moore-Coulomb failure criterion. If you assume a cohesionless soil, so this goes away, this disappears, and then you can draw this yellow line, which basically means that if you set a K naught, let's say in the K naught procedure, and it will be lower than this, it will be below the yellow line, it will be out of the Moore-Coulomb criterion, because of course if we have K naught equals to 1, we have the same vertical and the same horizontal stresses, and which means the stress state is isotropic, and for isotropic isotropic stress you won't reach the Moore-Coulomb failure criterion in compression, of course. So I think this is useful if you use the K naught procedure and you use the Moore-Coulomb model. It's used to check that your either entered or resulting K naught is not lower than it's not below this yellow line. And sometimes the same if you run the K naught procedure and you let the software compute the K naught from the Poisson ratio. So this means the same. You should not have a lower Poisson ratio than this value when you have this Moore-Coulomb this internal friction angle, because again you would end up out of the elastic domain in the second stage. And this is just a short note about this is sort of some convenient feature in the software that can prescribe a depth-dependent stiffness according this formula. So you can basically, because from ChemClay, for example, you know that the bulk modulus depends on current stress. You can use these formulas to, let's say, guess how the stiffness evolves, how the stiffness increases with depth, and use a known kappa for some first guess for this KD if you want to use this feature. So, and finally, the last thing that I would like to cover is to mention how the calibration works. So for Moore-Coulomb is quite standard. You perform an Endometric test. You get this Endometric modulus and Endometric modulus for unloading, reloading. Of course, you should select some reasonable stress level for which to express these two. It depends on your application, and then you receive angle of internal friction and cohesion from a triaxial or maybe a direct shear test. And if you have just a direct shear test, you have to estimate somehow Poisson ratio and then use the Poisson ratio to get the Young's modulus out of this Endometric modulus that you have measured in the Endometric test. But if you did the axial test, you can obtain shear modulus and use Endometric modulus and shear modulus to receive to calculate Young's modulus and Poisson ratio. And finally, if you want to calculate, or if you want to calibrate a ChemClay model or the hypoplastic model for clay, the procedure is quite. It's definitely more complicated than for the Morculomb model, and this is what we have covered in a project that I work as Czech Technical University, and together with Charles University, we had this project, and we created automatic calibration application, which is freely available on this website. So if you go to soil models website, it's hosted over here in software, calibration, software, and you have to create account and log in. And if you go to Excalibur, you can read about what it does. And finally, you open it over here. And this works. You can go to automatic calibration, which basically means that it works like this. You first download a LAF protocol, which is some Excel spreadsheet. And here in this Excel spreadsheet, you basically enter this Endometric data or some triaxial data over here. There has to be at least one endometer and at least one triaxial. If you have triaxials on natural and or reconstituted sample, it is an advantage, and we will get better results. But you don't have to enter them. And so you have this spreadsheet. You edit your spreadsheet, and then you go back to the web application and just browse to your file. And probably you choose one of these. This is the template. Choose which model you wish to calibrate. You accept the terms of use, which basically means that we will use your data in anonymous way to develop the software and to let's say improve this calibration as well. So we store these data, but we don't put them to anybody else. And then you write the calibration, and it basically computes, let's say, numerically some derivatives, some slopes of this model of these charts, and it does some optimization as well. So it's some hybrid, direct, and just optimization. And you receive your optimal values, and of course you can check what you have input and how the model calibrated fits your data. So you can use this if you want to calibrate the modified ChemClay or the hypoplastic clay. Okay, so let me go back to the presentation. Sorry, over here. And I think this concludes the webinar. So we have talked about a Morculomb model, which is suitable for strength critical applications. But you have to pay attention to either Poisson ratio or Young's modulus in terms of stiffness, because the stiffness is linear, and as we saw, stiffness of real soil is not linear. Another possibility is to use models of critical state that cover this behavior, the dilatation and compression of the soil, as we saw. if you want to calibrate these, you can use this web application. And of course, when you have calibrated either the molecular model or one of these models, you can run your odometer and triaxial test, or you can simulate these tests directly in GEO5 FEM and compare your results to what you get from the geotechnical laboratory to your data. Okay, so thank you very much for attention. And this concludes the webinar. And if there are any questions, please ask. So I can go, you can raise your hand if you want to participate in a discussion, or I can go to this Q&As. Okay, so first question, is it possible to establish a reliable relationship between CAD and CUP results for different type of soil? Okay, this means a relationship. I think not. It is not possible just to the stress path in one and the other. I mean, drained and undrained triaxial test is different. So you cannot, let's say, take results from the laboratory of one test and then create the results from the other test. These are two different tests, two different stress paths. But you definitely can use one to calibrate the model, and then you can simulate the other type of the laboratory test. This would be possible. So the second question is in Czech. Okay, so this question is about what are these E moduli in GEO5? What is Endometric modulus? What is Young's modulus? What is elastic modulus? What is the unloading reloading modulus, and etc. So there are two different types of moduli in terms of theory of elasticity, which cannot be mixed. One is Young's modulus, and the other is Endometric modulus. These are related. These are related by, how do I do? Okay, by these formulas. These formulas. Okay. So Endometric and Young's modulus, these are related by this formula, and the question always is, what should be the Young's modulus? Young's modulus can be the so-called deformation modulus, which is the primary, let's say, the modulus for the primary loading. This is what is at least in our region called sometimes a deformation modulus. So this would be the Young's modulus, and the unloading reloading modulus would be has to be higher, and there is a rule of thumb that it should be, let's say, 2 times, 3 times higher, maybe 5 times for some kind of soils. So so the Endometric modulus is not entered anywhere in the software, with the exception of the modified elastic model, but I think this is just exception. In the molecular model, you always enter the Young's modulus. So if you have Endometric modulus, you have to recalculate, and with this formula. But you can see that if we have some normal common values of Poisson ratio between 0.3 and 0.4, this is what I typically see for soils. It is somewhere between 1 and 2, the ratio of these. Okay, so I hope this answers the question. So hello, can you recommend when, in what case it is advisable to use geostatic stress calculations and when K-knot procedure? Okay, so when to use which type of or how to generate this this geostatic stress. So I would generally suggest to go with the default value, which means the calculation of the geostatic stress and not the K-knot procedure. But in some cases, for example, for heavily consolidated soils, when you know that the lateral stress is definitely by some measurements, you know it's higher than it would result from the normal analysis. So in this case, I would suggest to use a K-knot procedure. So you typically know what the lateral stress would be, and when you run normal analysis, or you can run normal analysis, and if you are not satisfied with the lateral stress, you can prescribe it somehow, but you have to do it reasonably, so you end up with some stress state that is admissible within the constitutive model that you will use in the second stage, because in the first stage you are not using any model, you just prescribe the stress. So I hope this answered the question. Okay, the question is, I had a different meeting and I was late where I could get a recorded presentation. Anyone who has registered for this webinar will receive a follow-up email, and you will receive this presentation, the models that we have created, and the recording, or there will be a link to, I think, YouTube recording. And it looks like that's it. So thank you for your attention, and yeah, this concludes the webinar. Thank you very much, and I hope you will enjoy us in the future again. Thank you very much.